All right, so now we're going to talk about the Boltzmann machine with hidden units. Okay, and so the Boltzmann machine basically is a stochastic model. Um, which has binary vector random variables. Okay, so let's say x, right? So x is x1 to xn. It's like with each of these components, it's like is binary, 0, 1. So this comes from a model of a spin system in physics. So this comes from a model of spin systems in physics. And it's also a model of memory in machine learning. Okay. So basically, it's like what's happening then is that you have a Markov chain. So you consider a Markov chain. So x1, and so on, right? Where the state at the new time, x, say k plus 1, at time k plus 1 is determined stochastically from the previous value, xk. So we're not going to describe how this sort of stochastic transition is achieved, right? But we're going to study the steady state problem. So we'll not consider sort of the stochastic dynamics of the state transition. But we're going to look at the stationary distribution. But we'll study the stable distribution. Okay, and this distribution is given by the following. So this is P, X, and it depends on A and W, right? And it's given by the exponential of A dot X minus 1/2 X transpose WX. So that's a quadratic term, and then there's a linear term, right? Minus phi of A and W, right? So this is called the Boltzmann machine. Okay, and then it's specified by these parameters. Because C, which is W and A. Okay, and then so what's going to happen is that this W is going to be a matrix, as you can sort of see here. And you can sort of imagine that the matrix W is measuring sort of the connectivity, it's like between the components. Okay, so the matrix W, right, is sort of a connection intensity, or sort of represents the interconnection intensity between sort of units I and j, right? So Wij denotes that. Okay, and then this matrix is symmetric. And there's an assumption that there's no self-interaction, which means that the diagonal is 0. Okay, so the symmetry means that the connection between I and j is equal to the connection between j and I, and then it's like the no self interaction part means that the diagonal term vanishes. Okay, so that just means that Wij is equal to Wji, and Wii equals to 0. Right? Okay, so this term here is what's called the bias term. And then what it does, as the name implies, is that it biases, it's like this sequence to be either close to 1 or 0. Okay? All right. So as before, we're going to think of this now as a hidden, that's like a sort of a problem with hidden variables. Okay, so we're going to let x again be partitioned into two parts, yh, where y is observable and h is hidden. And then for simplicity, we're going to consider what is called the restricted Boltzmann machine. Okay, so it's RBM. So what's going to happen then is that it consists of two layers. And the first layer, it's like has to do with the observable layer, and the second layer has to do with the hidden layer. Okay, so one is observable, one is hidden. And then the interactions, it's like only between the observable and hidden. It's like, and there's no coupling between the hidden variables, and there's no coupling between the observable variables. Okay, so connections are only between the layers. Okay, so let's sort of think of a picture like this. So say these are the hidden variables, and then this is the observable ones. Right, so this is H, this is Y. It doesn't necessarily. Okay, and then you could have interconnections, it's like between them. Right, but this is essentially a bipartite graph, right? So there are no connections, it's like between hidden variables nodes, and there are no connections between the observable nodes. So there's only a connection between a hidden node and an observable node. Okay. All right. So with that in mind, I can write down the stable distribution associated with this. And then for simplicity, I'm going to ignore the bias term. I'm just going to have, it's like the remaining terms. Okay. All right. So the stable distribution is P, Y, H, and then W. So I'm going to ignore the bias term. So that means that A is equal to 0. Right, so that's equal to the exponential of negative 1/2 y transpose WH. Right, so the fact that the connections, right, are between hidden variables and the observable variables together with the symmetry of W means that I can write that quadratic form, which normally involves both y and h, in this way, right? Okay. Right, so basically they're only, I mean, normally what you would have done is that you would have written this as something like YH transpose W YH, right? And in particular, I would have written this as WYY, for example, YH, WHY, and WHH, so to speak, right? And then YH. And then the fact that there are no, that this is a bipartite graph means that this term is 0 and this term is 0. And then the fact that this is symmetric means that these matrices are transposes of each other. All right, so I can rewrite a term like this. It's like into something which looks like this, right? Where this W here is like the WYH term here. Okay, anyway, so hopefully it's like that's clear. All right, so why I can write it like that. Okay, so as I said, we ignored the bias term and set it equal to 0. Okay, so then the marginal distribution of y is just py yw is equal to the sum over h of exponential of 1/2 y transpose wh minus psi of w, okay, which is a mixture of exponential family distributions. Okay, all right. So the conditional distribution okay, pH condition done y, depending on w, right, is equal to py h w divided by this marginal. Right, where the parameters w are known. Okay, and so this shows up in deep learning. This model sort of arises in deep learning, and can be studied, can also be studied from the viewpoint of Bayesian information geometry. Okay, anyway, so again, this is sort of an example. It's like of a situation where you have a statistical model. It's like with both observable and hidden variables. And with that in mind, it's like we're going to next address the question of how do you go about, it's like minimizing the distance between a model manifold. It's like which is sort of the set of probability distributions you expect the real distribution to be. It's like coming from, and then it's like the data. It's like manifold, which represents, it's like the set of observations, if you will, it's like which are compatible, it's like with the data which you've taken. Okay, so and as we'll see, it's like later that's in order to actually compute that, it's like you take advantage of this EM algorithm, which involves this alternating projection type method. Okay, so let me just stop here for now.